Okay, welcome to the July East Bay Astronomical Society General Meeting. I'm Rich Ozer, President of the EAS, and we have a special treat tonight. In addition to our regular speaker, Elinor Gates, who will be talking at 7:30, we have Sujay Nair, who is an EAS member. He is a student at the Stanford Online High School. He's in 11th grade. He has an interest in exoplanets. He's given presentations to the American Astronomical Society, and he's been published by the Astronomical Society of the Pacific. And his talk tonight is going to be about updating the mid-transit times of exoplanets and the citizen science opportunities for doing so. And Sujay will explain why that's important and how that affects access to observatory time in major observatories, how citizen science can contribute to optimizing the allocation of scarce resources for astronomy. So I'm going to not waste any more time and ask Sujay to turn on his mic and video, and we'll get started. Excellent. There you are. Thank you, Sujay. I will mute myself, and why don't you say hello and make sure we can hear you?
Yeah, can you all hear me?
Oh, yeah, there we go. Okay. Go.
All right. So, yeah, I'm Sujay Nair. Yeah, I'm going to be in the 11th grade at Stanford Online High School. And for the past 8 months or so, I've been studying exoplanets. So today I'll just be presenting on exoplanets and the importance of continuously observing them. And if you're interested, how you can get involved in groups doing this. So, well, what are exoplanets? Well, exoplanets are planets that orbit stars other than our sun. So in essence, exoplanets are just planets outside of our solar system. And so exoplanets can be as small or smaller than our moon, or they can be much, much bigger than Jupiter. So as of right now, there have been over 4,000 exoplanets confirmed, but there are thousands more candidates that are awaiting confirmation. But exoplanets aren't rare. As a matter of fact, they're everywhere. Just as an example, the spacecraft Kepler looked in one small field of view, I think it was around 0.25% of the sky. And in this small field of view, it discovered over 2,600 exoplanets. So in general, there are many ways of many methods of discovering exoplanets. I think some of the most common are the transit method, the astrometry method, and the radial velocity method. But this just shows that there are so many exoplanets out there to be found. So arguably the most common way and arguably the most straightforward way of detecting exoplanets is by the transit method. And an exoplanet's transit is when the planet comes in front of its host star, blocking some of the star's light. So the transit method involves plotting the relative brightness of the exoplanet's star against a comparison star over time to make what is known as a light curve. And an example light curve can be seen in the image. We use the relative brightness against the comparison star such that we can minimize the effects of the atmosphere, as the atmosphere will act on both the comparison star and the target star. And so from this light curve, periodic dips in brightness in the light curve can correspond to a planet coming in front of that host star. So the mid-transit time of an exoplanet is the time when the exoplanet is, well, in the middle of its transit, as shown in the image. The problem with this value is that it changes due to the uncertainty in the period of the planet. So because of that, it's extremely important for citizen scientists or amateur astronomers to observe and calculate new mid-transit times for the exoplanet, because incorrect times can hinder observations from large telescopes and future missions. An example is each minute of wasted time on the upcoming James Webb Space Telescope can cost thousands of dollars. So it's really important to continuously update these mid-transit times, especially because to do so is not very difficult. Almost anyone can do it. So to create light curves and fit the new mid-transit time, we use the Exoplanet Transit Interpretation Code, also known as EXOTIC, which is a simple Python code from the group Exoplanet Watch, which is a project from NASA Jet Propulsion Lab. And I'll talk a little bit more about Exoplanet Watch soon. So we point EXOTIC to a directory of FITS files or images, or a pre-reduced text file. And from there, Exotic will output a light curve just like the one shown on the slide. Exotic has its own built-in photometry and can run on either your local machine or you can run it on the cloud with Google Collaboratory. So how exactly does a project like this work? Well, it's actually pretty simple. All of these projects will start with some images. The good thing about these images is they don't have to be from an expensive robotic telescope. They just need to track the target star over the course of a transit. And this adds to the fact that amateur astronomers are of great help to these studies. Moreover, Exotic will deal with misalignments and things like meridian flips itself, so there isn't too much to worry about. After getting the images, some of the most important things needed are the X and Y pixel coordinates of the target star and between 1 and 10 comparison stars. And that's where some image analysis comes in. Quickly on the note of the comparison stars, Exotic will go through and pick the best comparison star of all the up to 10 that you input. Okay, so now to get these pixel values, you can just open the image in a simple astronomical software. Like the one that I use is SAO DS9. And this displays the X and Y pixel coordinates wherever you put your mouse on the image. So once these and a few other straightforward parameters are inputted into Exotic, the reduction process begins. So after probably an hour or so, it'll have finished and you'll have a light curve like you see on the slide. Though when it comes to mid-transits, the light curve itself is not enough to give you, the light curve itself isn't enough. The light curve will just serve as well confidence whether or not Exotic fit the data properly. Though you can also just look at the uncertainty values, which will be outputted. To really analyze these results, you'll want to compare the mid-transit that Exotic calculates and outputs in a file like that last text file to the existing mid-transit on the NASA Exoplanet Archive or wherever it was last confirmed. And by doing this, you can learn about how off the mid-transit was by calculating something called the phase difference. And well, that's basically it. A study like this is something worth publishing, and for how important it is, it's not very hard. If you aren't someone who does a lot of imaging or observing, there's plenty of data out there needing reduction and analysis. If you're someone who has images, but you maybe don't want to reduce the data through Exotic, there's plenty of people who can reduce it for you, and you can use all these results in an academic study. So one simple example of a project is a study myself and one other did, which included the exoplanet HAP B23b. An astronomer known as Pat Boyce imaged this target for us with his less than 1 meter telescope. And we ended up with around 420 FITS files, each of which were around 2 megabytes. From there, we just needed to point Exotic to the directory containing all the images, and it just reduced the data and gave us this light curve. The only additional features that we added were some calibration frames like darks, flats, biases, but we added those through Exotic. As shown on the slide, you can see there's a pretty clear dip in brightness with low residuals. And so, well, after looking at the light curve, what we did is we compared the mid-transit time that Exotic outputted to the expected mid-transit time of the night based on the existing mid-transit on the NASA Exoplanet Archive. And we saw a difference of around 20 minutes. So that told us that this midpoint was slightly off. So this result was then published along with a few other planets. Another example includes some of my research on the exoplanet KPS-1b, which is also known as the test object of interest 1780.01. Similar to the previous planet, this planet was imaged by another owner of a really small telescope. In this case, however, there were only 101 FITS files, and there were no additional calibration frames to be added. Though this didn't seem to cause any problems with Exotic, as well, no errors were received, and we can see again a dip in the light curve. After comparing Exotic's outputted mid-transit time and the accepted mid-transit time from the test project and the NASA Exoplanet Archive, we saw again here a difference from expected mid-transit of around 22 minutes. And this is all interesting because this target is a test object of interest. So its transit properties such as transit depth or duration, they may not be that ideal for something like a nice clean light curve. However, those values, at least from what we can see in the light curve, are pretty accurate. Another study worth noting is one done with HAP P3b. So here data were requested and obtained from the Las Cumbres Observatory 0.4 meter robotic telescopes. We received 370 FITS files, which we then let Exotic run on. The problem here was that after running on the FITS files a few times, we were getting really unclear light curves. Because of this, we decided to try pre-reduced text files, which we got from the Our Solar Siblings pipeline. which we then fed into Exotic. The light curve from our best two reduced text files can be seen in the two leftmost images. Though the problem was we ended up with varying mid-transit differences based on the reduction algorithm. And we were also not completely satisfied as well. The light curves are not the cleanest looking. During our creation of the not so good light curves in the beginning, we were getting some warning messages Exotic was prompting us about certain images in the data. So after removing these images, we got the light curve on the right. And this gave us a slightly different mid-transit difference with higher confidence in the measurement, which we then published. The last example I want to give of is of the exoplanet Qatar 1b. So like with HAT P23b, Pat Boyce imaged this for us with his less than 1 meter telescope. Here we had 300 FITS files, though the unique problem with this data set was that, well, the data contained a meridian flip. Now this is when the telescope, as it's tracking the star, has to rotate 180 degrees due to that star crossing the meridian, as we would say. So at that time, during this time when we reduced the data, Exotic itself didn't account for this. So we combined separate relative flux text files from both sides of the flip to get the light curve on the slide. But now Exotic will automatically fix any alignment issues. And well, the fit itself was pretty good with low scatter, though we ended up with a mid-transit being off with around 30 minutes. So it was great that we ended up with a clean fit such that we can then have confidence in this value and publish it. So how would one get involved with all these projects? So all you need to do is go to the Exoplanet Watch NASA website, where there are plenty of directions how to get involved. You can also just directly reach out to the official Exoplanet Watch email on the slide. Once you're ready to do research, there are plenty of observers on Exoplanet Watch that should have a good amount of data to be reduced. Also, if you are an observer, there'll be plenty of people who'd be happy to reduce your data if you don't want to. Overall, feel free to reach out to me as well at the email at the bottom, and I'd also be happy to connect you directly. So in conclusion, it's really important to continuously observe exoplanets and calculate new mid-transit times, because that info changes and it's not hard to fix. Doing so can save extremely valuable time on large telescopes and big space missions. And it's also a great opportunity for citizen scientists or amateur astronomers to get involved. To get involved and contribute, whether it be through a research paper or publishing results on the AAVSO, or even just getting and reducing data. It's a great opportunity. So lastly, I just included the emails again at the bottom. And if you ever need help with a project like this, feel free to reach out and I'd be glad to help. Thanks.
Thank you, Sujay. Hey, I got a couple of questions for you. So what type, if an amateur wants to get involved, let's say we have an amateur astronomer who has the necessary equipment to be able to find a particular star that is an exoplanet candidate, and we wanted to be updating the midpoint transit time. What type of photometry equipment is necessary to do this, or are you just using a camera and estimating it against known stars, or are people doing it just with visual estimation? What's required in the way of equipment?
Right. So I believe a setup could be relatively cheap. I don't think any external photometry is necessary, because
hold on, you're cutting out there. If you could, you're cutting out. Yeah, if you can repeat the last sentence.
Sorry. Can you hear me okay now?
Yes.
Okay. So I was just saying, these equipments, they don't have to be extremely expensive or anything. All you need is a set of time series data or just a bunch of images. And Exotic, the Python code, has its own built-in photometry where it'll go over your images and it'll do it all for you. So
you send the images in, and it will reduce the data based on surrounding stars and figure it out if you haven't blown the stars out.
Right.
With too long an exposure.
Yeah, these don't have to be pristine images either. Exotic can still create a decent light curve with uncalibrated images, or as long as they're tracking the star and the amount of misalignments aren't huge, then it should be good.
Great. Well, that's very interesting. If anybody else has any questions, now's a good time to throw them into the chat window. We do see anything that you type into the chat. I'll check real quick to see if anybody has asked on Facebook. I don't think so. Not at this time. So just stay here for a minute, and we'll see if anybody asks any questions.
Sure.
And then we'll move on to some club announcements in the meantime. Oh, what are all the awards behind you?
Just, from like external activities, like for example, chess, they love to give out grand trophies like that. So, most of those are like my brothers as well. So.
Okay, they're all in one place so they don't get lost. Yeah, okay, great. And a lot of people saying that they appreciate your talk, and I certainly did. So just a couple of announcements. As you know, a lot of our activities have been curtailed by the state of the world. Chabot is still closed, but you should be aware that the Chabot Space and Science Center is putting online activities up every week, usually Friday and Saturday nights. In fact, after the talk tonight, Gerald and I will be doing virtual telescope viewing again from Nellie, and that starts at 9:30. If you're interested in that, you can go to the Chabot page on Facebook and go to the live video section, and it will pop up at 9:30, and you could see whatever we're going to be pointing Nellie at tonight. Other announcements regarding any future openings at Chabot, again, that is undetermined until we get a handle on what the COVID pandemic looks like. Chabot is not going to be taking any chances and allowing visitors to the Science Center. So all of these things are on hold right now. It's an unfortunate reality of our times. However, if you do want to get out and see the comet, you can see behind me is my image of the comet that I took the other night, the other morning. And this was at 4:45 in the morning, so you have to get up really early. But the orbit of this comet is such that in another week and a half, it's going to be an evening object right after sunset. And the closest approach to Earth will be July 22nd. So for those of you who don't like getting up really early in the morning and driving to a dark location, you can do that now at normal human hours and leave home and get to some dark place by sunset and look at the comet then. So this is Comet Neowise, and it's actually, it's the nicest comet I've ever seen. I missed Halley's comet when it came by, so this is the next best thing for me. Let's see, there are a couple of other questions, I think. Let's see if any of these are for you. Oh, Sujay, how did you first get interested in investigating exoplanets?
Oh, yeah, that's a good question. Well, this last year, I at school, I took an astrophysics course, and well, I was really interested in, well, everything, but I wanted to, kind of start to do research, figure new things out, and do something that would be interesting or impactful. And so my teacher had linked me with this group, Exoplanet Watch, and talked a lot about like how simple it is to do this, and how even a lot of other high school students can get involved. And so, yeah, that was it for me. Since then, I've just been doing more and more with this.
It's great. It's great. Your enthusiasm is excellent, and it's really a pleasure to see. Somebody asked how they may share this later on. This will be on our Facebook page in the video section immediately after the presentation concludes, and we will be then moving the entire thing, or at least copying the entire thing, to our YouTube channel, a link for which is on the East Bay Astronomical Society website. So there'll be a couple of places we can find the video. This is the first time I'm relying on Facebook for recording the video properly, and we'll see how that goes, because I didn't want to run out of space on the Zoom recording feature, which has been a little bit of a problem. I guess that's it, Sujay. Thank you so much. I'm going to ask you to turn off your video and audio. You could stay on the Zoom meeting if you'd like to hear the rest of the presentation tonight. And I'm going to ask Dave and Elinor to join in with their audio and video, and then I'm going to bow out.
Okay.
And Elinor, I need your video. Or you
yeah, it is unfortunately again saying
okay, hold on.
I can't start my video.
I will figure this out. I am going to make you a co-host. And
that did it. Thank you.
there we go. All right, so I'm going to bow out and leave it to both of you.
Oh, Rich, one thing I wanted you to mention is the possibility of future speakers as well before I get going.
Oh, yes. What we're working on is an astrophotography speaker for next month, and we'll be sending out more information. I'm hoping we get Rogelio Bernal Andreo. And the following month that would be September, I'd like to get a speaker to talk about what's going on at the Yerkes Observatory. And I'm looking to get Dan Kaler for that, and who was the one of the operators at the Yerkes and used to be an editor at Astronomy Magazine and has a long history with astronomy and amateur astronomers. So that's what we're working on. I can't promise any of that yet, but stay tuned. You'll get announcements. So
thank you very much, Rich.
Bye, everyone.
Before I get going, I just want to say how proud I am to have a member like Sujay I was a pretty active high school member, but boy, he totally blows me away. And I'm so impressed and I'm so proud to have somebody like that as a fellow member. Now, I'd like to also welcome Dr. Gates as our speaker tonight. Elinor, thank you very much for agreeing to speak to us. Elinor did her undergraduate work at Mount Holyoke College in mathematics and astrophysics. She got her PhD in physics and astronomy from the University of New Mexico. And then before she worked at Lick Observatory, she worked at Smithsonian Astrophysical Center. Elinor, thank you very much for taking very good care of asteroids. All of our asteroids are very nicely behaved, thank you. I always think of them as small children who have a tendency to misbehave at times. Elinor is going to speak to us tonight about Lick Observatory during the pandemic periods, both in 1918 and of course also now. It's a very topical subject. I just picked up my wife from work today and she just found out that possibly one of her coworkers might have COVID. So very, very interesting. It's like the ancient Chinese curse, when you live in interesting times. Before I get going, I just wanted to mention very briefly that Lick Observatory is very remarkable because it's the first mountaintop observatory in history. We all think of that as being very natural, but Lick was the first one to do it. And also that Lick is named after James Lick, who I believe made a fortune in, I think, the gold rush or something like that. And Lick's original intent was to construct a giant pyramid in the middle of Market Street in his honor. And then a friend of his said to him, why don't you donate your money to an observatory? That way every discovery will have your name on it and you will be immortalized. And he liked that idea, but he also decided he wanted to have his body buried there under the observatory. And as I understand that he occasionally makes his odoriferous presence aware possible. Anyway, so without any further ado, I'd like to introduce our wonderful guest speaker tonight, Dr. Elinor Gates. Go ahead, Elinor.
Okay, thank you very much. Let me share my screen here. Oops, share screen go. So thank you for that wonderful introduction. And I, of course, also have to show off my image of Comet Neowise here that I took a few mornings ago. But yeah, when the whole pandemic started in 2020, it really made me think, how did things go back in 1918? How did the pandemic back then affect Lick Observatory and the research, and what were the hot research topics of the day. So it was really fun for me to go back and look into the history of Lick Observatory, as well as talk to you today about how we're dealing with the pandemic now and how we're coping and maintaining to do research, at least in some capacity. But first, I want to give you an idea of where Lick Observatory is, for those of you who haven't visited us. We sit on the highest peak in the San Francisco Bay Area, Mount Hamilton, east of San Jose. And I've labeled many of the telescopes that are currently here. I won't mention all of them during the talk, but many of them will be mentioned somewhere along the line. And as Dave mentioned in the introduction, we were the first year-round accessible mountaintop observatory, and James Lick was very adamant about that he was not only going to have the greatest telescope in the world, but that it would be usable all the time. James Lick made his money during the gold rush in real estate. He actually arrived in California 2 weeks before gold was discovered, and people thought he was nuts for buying up all this land, but it proved to be a wise investment. He became the richest man in California by the 1860s, and of his over $3 million fortune, he decided $700,000 would go to build his telescope as a monument to himself. And he is indeed buried at the base of the 36-inch refractor, which was the largest telescope of its kind when it was constructed in the 1880s. Sadly, James Lick never lived to see his telescope. He died in 1876. He was buried in the Masonic Cemetery, and in 1887, when they were about ready to install the telescope, they disinterred him from San Francisco and put him in his final resting place up here on Mount Hamilton underneath the telescope. So almost immediately, the 36-inch telescope proved its worth. They were planning to have the first light party on January 1st. Unfortunately, there was poor weather. By January 3rd, the weather had cleared. They were able to open up the dome, and they calculated what star would be visible through the open slit, because unfortunately the dome was still frozen shut in position, and they couldn't move it. So, but they looked at it, they found Aldebaran, and then they tried to focus the telescope, and they discovered that they had inadvertently mismeasured the focal length of the telescope. It was about 6 inches too long. So over the intervening many days of poor weather, they fixed the telescope, and on January 7th, James Keeler did the first science observation with the 36-inch refractor. And he looked at Saturn. And in that first view, he discovered a new gap in the rings of Saturn that he dubbed the Encke gap. Later on with Voyager, another gap was discovered that was named in Keeler's honor nearby. But immediately, Lick Observatory proved its worth as having the greatest telescope in the world. Not too long thereafter, Edward Emerson Barnard discovered the fifth moon of Jupiter, Amalthea. Before that, only the 4 giant moons discovered by Galileo, Io, Europa, Callisto, and Ganymede, were known. And that was about 300 years between that discovery and Edward Emerson Barnard's discovery. It turns out Amalthea was the last moon in our solar system discovered using visual techniques, meaning looking through an eyepiece. All moons in our solar system discovered later were discovered using photographic techniques. But E.E. Barnard was a wonderful artist. You can see in his logbook the beautiful details of Jupiter and the moons that he drew as part of his discovery. Edward Holden was the first director of Lick Observatory, and he was using the 36-inch refractor to study the moon. And his intent was to take pictures of the moon at all different phases, because along the terminator, the line between the night and day sides, you get very high contrast images on the craters and the mountains of the moon. And he wanted to assemble them all into a very high contrast image. And the moon images from the 36-inch refractor were just the finest images available of the moon in the world, and were used in textbooks until reasonably recently as a standard. Just a couple months ago, an amateur astronomer, Andrew McCarthy, essentially did the same thing, taking the moon images at all the different phases and combining all the terminator images to make this really incredible high contrast image that I'm sure Edward Holden would have been very pleased with should he see it today. Anyway, now we're going to move forward a couple decades in the history of Lick Observatory and talk about the Spanish flu. And really, the beginning of the Spanish flu really starts with when the US entered World War I in 1917. Now, World War I actually began in 1914, and it took many years before the US got involved. And by June of 1917, they instituted a draft. And this actually affected Lick Observatory directly because many of the younger astronomers, students, were drafted to fight in World War I. And the more senior astronomers with their technical expertise were volunteering to help with the war effort. So they were taking their technical skills and working to help our soldiers in the war. So that left Lick Observatory somewhat depopulated in terms of the available staff. So a lot of the work was picked up by the older senior astronomers who working on the war effort, as well as some of the lady computers and women astronomers of Lick Observatory. Anyway, by March of 1918, there were many outbreaks of flu detected in the US. By April, there had been the first deaths, but really the worst of it was the second wave of the Spanish flu, where by September of 1918, they had over 14,000 flu cases at Camp Devens outside of Boston alone. And people were told if you were sick, stay home, quarantine yourself. By October 1918, 195,000 Americans died of the flu during that month alone. There was a severe shortage of nurses. They were using cold storage plants as temporary morgues. Large cities were closing schools, theaters, movie houses, prohibiting public gatherings. And San Francisco Board of Health required anybody serving the public to wear masks and was encouraging everyone to wear face masks. This all sounds kind of scarily familiar compared to what we're going through right now, but very, very severe. Whoops, sorry about that. By November of 1918, finally World War I ended, but with all the returning soldiers from Europe, they brought the influenza back with them from Europe, where the pandemic was still raging. And by January of 1919, the third wave of the flu happened. And just in San Francisco alone, in the first 5 days of January 1919, there were 1,800 flu cases and 101 deaths. By February, it seemed to be abating and things were getting back to normal here in the United States. But President Woodrow Wilson had gone to France, where the flu was still rampant, to the Versailles Peace Conference, and he collapsed. And they believe it's because he was weak from having the flu. So, very, very serious pandemic. And all told, the death toll from the Spanish flu is estimated to be somewhere between 20 and 50 million people. So let's hope this current pandemic does not get that bad. Luckily, we have modern medicine and stuff to help us along that was not available back in 1918. Anyway, what did Lick Observatory look like back in 1918? Well, I have a lovely aerial shot of Lick Observatory from Google, and essentially downtown Mount Hamilton right here, everything east of that is all new in this photograph. None of those buildings existed. There were a few buildings east of what we call downtown Mount Hamilton, but they were barns for the horses, workshops, maybe a few houses. But the east side of the mountain, the west side of the mountain looks very much today like it did back in 1918. You have the main building here with the 36-inch Lick refractor. At the south end of the building, we had that. Back then they had a 12-inch Clark refractor. At the north end, the astronomers' dormitory had been built in 1912, so it was a relatively new building. This building here, the lab and measurement building, as we call it, didn't exist. Instead, there was a meridian circle that you can see on the drawing to the right here. And there's a picture of it here at the lower left. And that meridian circle was a very important instrument back then because they would look at the stars and measure exactly what time certain stars were crossing the meridian. And they would provide this accurate timing to the train station so that the trains would run on time, and to the post office and other similar organizations, as well as doing other astronomical research. The Crosley telescope had also been erected. It was a 36-inch reflecting telescope, as well as Edward Emerson Barnard lived in this house here, built in 1894, and Edward Holden, not Edward Holden, William Wallace Campbell, who would later become the director of Lick Observatory, lived in this other building. I'm actually broadcasting today to you from the old director's house here on Mount Hamilton. So it was a very different looking place, a lot fewer telescopes back then. But one of the big, exciting research topics of 1918 was trying to confirm Einstein's theory of relativity using a total solar eclipse. And they were fortunate that in 1918 in Goldendale, Washington, there was going to be a total solar eclipse. Now, back in 1918, they didn't have the travel bans and restrictions that we have today because people in general were a lot less mobile. And in fact, Lick Observatory was saved from most of the ravages of the Spanish flu due to its remoteness. Only one family on Mount Hamilton at that time, Director Campbell's family, had an automobile. Everyone else had relied on the Mount Hamilton stage to bring up groceries from town or the mail. So very different times. So there was no restriction from trying to go to Goldendale to do this measurement. Now, how do you measure or test Einstein's theory of relativity? Well, during a total solar eclipse, when the sun is blocked, you can actually see the stars around it. And what you do is you measure the positions of those stars because the sun's gravity, according to the theory of relativity, will cause the light to bend around the sun and change the positions of the stars because of that gravitational well, compared to measurements of the positions of stars, say 6 months earlier when the sun is not in the way. Heber Curtis, one of the astronomers, he volunteered for the war effort, was using his technical expertise, but he got a release from the military to participate in this measurement process, and he designed these lovely glass scales that are in our historical archive up here, very accurate measuring scales so that he could measure the positions of these stars. Unfortunately, they didn't get good enough data with this eclipse, and there are two reasons for this. One is that they tried to do this measurement back in 1914 with a total solar eclipse in the Ukraine. And they had traveled with all their equipment to Europe, to the Ukraine, set it up, and then they had terrible weather. And so they didn't see the eclipse. They couldn't get any data. While they were there, World War I began. And the researchers from Lick Observatory were supposed to travel back to the United States via Germany. Of course, that, with the outbreak of World War I, was not possible. So they had to leave all their equipment there in Russia with trusted colleagues while they went through Finland and quite a circuitous route to get back to the United States. It turns out their very best equipment did not make it back to the United States in time for the 1918 eclipse. Luckily, they had other equipment available, and they actually borrowed some lenses from Chabot Observatory to create their solar telescope for the 1918 eclipse. Unfortunately, that eclipse was also plagued with poor weather, but they did get to see it. It was cloudy until a couple minutes right before the eclipse. Then the skies opened up. They took a few photographs, and then at the end of the eclipse, the clouds closed back in again. So because they didn't have their good lenses from their good equipment and the weather didn't cooperate, they were unable to confirm Einstein's theory of relativity with the 1918 eclipse. That would have to wait till Eddington in 1919, and then the final definitive confirmation by Lick Observatory astronomer William Wallace Campbell in Australia in 1922. However, even though they failed at their main objective, they were able to do other important science on the sun. And that was partly timing. Mr. Tucker was an astronomer here at Lick Observatory, and he was using the Meridian Circle telescope that I showed on the previous slide to make accurate measurements of the moon's position. And he determined that actually the solar eclipse would occur about 20 seconds earlier than predicted in the Nautical Almanac. And indeed, when they went to the site and measured precisely the timing of the eclipse, it happened 16.6 seconds in advance of the almanac prediction. So Mr. Tucker's measurements were correct. They fine-tuned the orbits of the moon. Lots of good things came out of that. They were also looking at the corona, both looking at the spectra of the corona and the polarization. So they were, with the coronagraph, they had a plate grating with over 14,000 lines per inch that would take the light of the sun and spread it out into a spectrum, much like a prism will take light and white light from the sun and make a rainbow. And if you look at the pictures here, the big wide stripe in the middle here, I hope you all can see my cursor, is the solar spectrum with some absorption lines from calcium and hydrogen, the expected spectrum. And then above it, here's the coronal spectrum. So you can see some bright emission lines from hydrogen beta, calcium. Over here, you can see the relative strengths. Now, they didn't know the source of all the elements that were causing these emission lines in the corona. And, they knew some of them, the hydrogen and calcium. But there's this one weird line called the green coronal line that's shown in the bottom spectrum. And you can see it's pretty bright here, pretty distinct. And one of the things they were able to do in 1918 was definitively measure the wavelength of this with high enough accuracy to know it really is at 5303 angstrom wavelength. So it's in the green. We still call it the green coronal line today, but they didn't know what caused it. You'll see these little hashes above and below your spectrum. Those are your iron comparison spectrum for an iron arc lamp. We now today know that that green coronal line comes from very highly ionized iron. And they just didn't have the technology back in 1918 to ionize iron that extremely to know that's what it came from. But this iron line, this green coronal line, is kind of squirrely. We don't quite know why in some spectra it comes up quite strongly, like in 1918. And today, or say in this sample, more modern spectrum from 2008, that it's essentially not visible at all. It may be associated with the solar magnetic cycle. There may be other reasons. Anyway, we don't quite fully understand the physics of the corona even today. So we're still working on it. Also, one of the things they wanted to measure was the polarization of the corona. And so they used a double image camera with an achromatic lens and put in front of it a calcite cube. And you can see here a picture of the calcite cube. And light of different polarizations goes through the calcite cube in slightly different paths. So you get two images of different polarizations. And one of the things that polarized light, light tends to get polarized when it bounces off things. So that, your polarized sunglasses work so well because light gets polarized when it bounces off the pavement or water or snow. And so if you have your polarized sunglasses aligned the right way, it blocks that bounced light and gives you a clearer view. But they looked at both green and blue light from this corona. And it turned out that the blue light was more polarized than the green light. And that implies that, scattering increases as the wavelength of light decreases, meaning blue light scatters more readily. Now we see this in our own atmosphere because the sky is blue, because the blue light from the sun scatters more readily than the longer wavelengths like green or red. And the key thing they discovered is where the scattering of light and polarization is happening. And they determined that it was happening at a distance of more than 800,000 miles from the edge of the sun. So that was the first time they sort of had a good measurement of where these particles that are causing the scattering are located. So lots of fundamental stuff there. Other research that was being done at that time was spectroscopic binary stars. These are two stars that orbit around each other. And Lick Observatory back in 1918 had a southern station, a southern expedition funded by Donald Mills, who was a wealthy businessman. And so we had a southern station in Chile, and Heber Curtis, among others, spent time down there. And one of their big projects was trying to measure the orbits of these binary stars. Now that's a highly challenging thing to do. So CARINAE is a 4.4 magnitude G5 star, and of these sample spectra here on the right, G5 is right here. You can see there aren't a lot of dark lines in it. So those dark lines are absorption of certain colors by the elements in the star's photosphere. And if you want to measure the orbit of a spectroscopic binary star, you look at these dark lines, and as the star moves in its orbit towards you, the dark lines shift a little bluewards. And as it moves away from you, they shift a little redwards. And you need to very accurately measure that. Now, they wanted to measure the speed of the star as it went around its companion to an accuracy of better than 1 kilometer per second. And that's a pretty slow speed. And just to give you a sense of how hard that measurement is to do, a 25 kilometer per second shift in the optical light is about a half angstrom change of wavelength. It's tiny. But they had a large telescope, 37-inch reflector with a spectrograph, and they measured this. And you can see CARINAE, say the right star here, they determined had a period of about 195 days and essentially a perfectly circular orbit, that this is absolutely beautiful sine wave going through these points. And you can see that the deviation is about plus or minus 25 kilometers per second. So they were looking at shifts on the order of much less than half an angstrom to make this measurement. In contrast, another star they looked at was Delta Columbae, similar magnitude G5 star, but in this case, much longer period. It took much longer to get all the data, many years. It's an 870-day period. But you can see highly elliptical orbit. It's not a nice sine wave. So the star essentially goes slowly around its companion and then whips around the close end and then goes out. So this highly elliptical orbit, or very oval orbit, was determined. And again, you can see all the total deviation of the spectra was about half an angstrom. So again, the highest resolution spectroscopy being done in the world was on these spectroscopic binaries back in 1918. Of course, the solar system objects were always a popular target for study. So Comet Shore was discovered in 1918 by Mr. Shore in Germany. And here's some pictures from 1918 of the comet. Not a hugely bright comet, but lots of data were taken from observers around the world, including Mr. Aitken at Lick Observatory. He later became director of Lick Observatory. And E.E. Barnard had hence moved to Yerkes Observatory and spent a lot of time. But between all the observers looking at this, they determined the period of this comet is 6.67 years. So it's a fairly short period comet. Never gets particularly bright, so that's why we don't see it every few years, giving us a wonderful tail like Comet Neowise is doing right now. They were also studying asteroids in our solar system. And this is a place where taking a lot of the data on these asteroids was being done by lady astronomers, both at Maria Mitchell Observatory with Miss Harwood doing a lot of research, but also Miss Young here at Lick Observatory was taking data. So whereas at this time period, the ladies at the Harvard College Observatory, like Henrietta Leavitt, were not allowed to use the telescopes. Lick Observatory and Maria Mitchell Observatory had women being very active in astronomy. And in fact, the first 2 PhDs granted to women at the University of California were granted to the lady astronomers here at Lick Observatory in 1913. So we're very proud of our history with lady astronomers and being more progressive. Anyway, asteroid ERIDA was discovered in 1911 by Leuschner, and he named it after his daughter ERIDA. And these lady astronomers took lovely data The data was analyzed by Mr. Jeffers, the supervisor of Miss Young here at Lick Observatory, and determined its period was 5.3 years. And today we know that it's a sizable asteroid of about 36 kilometer diameter. They didn't know the size of it back then, though. Anyway, another one of the big topics was the size and scale of the universe. So Heber Curtis, who I've already mentioned a couple times, was studying these spiral nebulae. And there was the great debate in 1920 that they were all preparing for with Heber Curtis at Lick Observatory versus Harlow Shapley at the Harvard College Observatory. And Heber Curtis had noticed that, along with James Keeler before him, that no matter where they looked, there were these little spiral nebulae in the background of their images. And Heber Curtis was of the opinion that these were other island universes and that they were very far away, whereas Harlow Shapley just couldn't imagine that the universe was that large and that these spiral nebulae had to be some phenomena inside our Milky Way galaxy. Of course, in the end, it turned out 100 years ago that Heber Curtis was correct and that these were other island universes that we now call galaxies. And it really expanded our understanding of the size and scale of the universe. So these were some of the hot topics of research, 100 years ago. Well, how are we doing today with the current pandemic? Well, let's go over a quick timeline of the current pandemic and its grim statistics. The first we knew of the pandemic was that at the end of December in 2019, that there was a cluster of unusual cases of pneumonia in Wuhan, China. And just a week later, the scientists in China identified it as a new novel coronavirus. Now, coronaviruses are very common. They cause the common cold. They've also covered other epidemics, such as the SARS epidemic in 2003 and MERS later on. So it's a very insidious sort of virus. It could be mild or severe disease. Anyway, by the 11th of January, the first death was recorded in Wuhan, China, of a 61-year-old man. But the next day, China had been very quick to discover the code, the genetic sequence of the novel coronavirus, and they shared it publicly with the rest of the world, giving the rest of the world a jump on trying to figure out how does this virus operate? How do we treat it? How do we create a vaccine? All those things that are very difficult to do. By late January, we had the first confirmed cases of the new coronavirus in Washington State. By the end of January, the World Health Organization did declare the global outbreak as a global health emergency. By early February, the death toll in China surpassed the fatalities from the SARS outbreak. And then a few days later, the World Health Organization announced that this disease now has an official name, that the virus is called SARS-CoV-2, and that the disease it causes is COVID-19. At the end of February, we had the first death of a man in Washington State in the United States. By early March, the global number of cases had gone up to 100,000. And this is when it became, I think, very real to most of us here in the United States as well, that we saw cases going up. People were getting sick all over the place. And by the 11th of March, the WHO declared it a pandemic and things started shutting down. And things I've highlighted in red in this timeline are things that affected Lick Observatory directly, decisions we made, or UC Santa Cruz, because that is where our business offices and administration are. But on March 11th, UC Santa Cruz suspended in-person classes to protect students and their staff from this new disease. So suddenly all of our astronomy faculty were scrambling, trying to change their courses and mentoring of students to be done online rather than in person. On the 12th of March, we here on the mountain decided that we needed to protect the public in our visitor center. So we started enhancing our cleaning, giving masks to our employees and gloves to wear, reducing the size of groups and allowing them to spread out more when we went into the 36-inch telescope for showings. And it also became obvious that we'd be unable to hold any of our April and May events. So some of these were public events, such as public evening tours. Some of them were private events like weddings. So, very challenging times. By the 13th of March, many states started announcing that they were going to plan to close schools for everyone's safety. And by the 14th of March, Lick Observatory, along with other museums in Santa Clara County, like the Tech Museum, decided that it was really wisest to close to the public and make sure that we protected people there. By March 17th, UC Santa Cruz decided that it was time to close campus to everyone except essential personnel, which means that we had to ramp down our research activities. We could not do observing as normal anymore here at the observatory. It's also the same day that Santa Clara County announced their shelter-in-place order. And of course, Lick Observatory sits in Santa Clara County. So we have to abide by all their public health rules. A few days later, on the 20th of March, California started its statewide stay-at-home order. And the number of cases at that time had just exceeded 1,000 cases in California. And what had really started is sort of Santa Clara County in the Bay Area is one of the epicenters, along with Washington State, of the coronavirus here in the US. It had now shifted to New York City, and they were getting hit very hard in New York, New Jersey, and Connecticut. By the end of March, we had over 500,000 cases in the world. The number of cases in the US was over 100,000. Early April, over 1 million cases in the world. By the 9th of April, New York had over 150,000 cases. That was more than any other country except the USA. So it was very, very grim. And of course, it became obvious at this point that Lick Observatory would not be able to hold any of our public events. So we had to cancel all our public programs and, of course, remain closed to the public. And of course, by mid-April, there were over 2 million cases. By the end of April, over 3 million cases. And now we'll just run forward a couple months to where we stood as of yesterday afternoon, that worldwide we have over 12.6 million cases of COVID, known confirmed cases, and over 560,000 deaths worldwide. 3.2 million of those cases are here in the US. We have over 135,000 deaths so far. And Brazil is now becoming a new epicenter with over 1.8 million cases and a lot of deaths. And Santa Clara County, for being one of the early hotspots, because it acted early, has actually had fewer cases and fewer deaths than you might expect for having the 10th largest city in the United States, San Jose, in our county. But it's still pretty grim statistics with nearly 6,000 cases and over 160 deaths so far. So how has Lick Observatory been dealing with it? Well, I highlighted a few of the decisions we made along the way, but as of starting March 13th, with new health orders and regulations coming out from the CDC and from the county, our leadership team decided we needed to have daily meetings to figure out how to deal with the new regulations, keep our staff and public and volunteers safe. So you can see one of our Zoom meetings here. Here we have Dr. Claire Max, the head of our Lick Observatory. Then we have Matthew Cetrone, our deputy director, Kostas Flores, our mountain superintendent in charge of the mountain facilities, Phil Heinz, head of the Laboratory for Adaptive Optics. So lots of people involved. And it was really challenging. There were daily meetings at 8:30 every morning. And of course, there were new regulations. We'd have a meeting at 8:30 and by noon or 5 p.m., something would have changed that we'd have to deal with. And that was the case for the first couple months. Then we shut down, switched about 3 or 4 weeks ago to having meetings only twice a week because things had sort of stabilized. And now, just this past week, we've switched to having once a week meetings, which may not be quite enough, we're discovering, because Santa Clara County sent out a new order for new paperwork to be filled in filled in for businesses. That should be done by Monday, apparently. So all sorts of challenges. Anyway, as I said, we closed our observatory to the public on March 14th. And then on March 17th, with the shutting down due to the shelter in place and the essential personnel only, the challenge was determining who are actually essential personnel. It turns out most of the staff here on the mountain of Mount Hamilton are essential personnel. So most of our staff are involved in the physical infrastructure of the facility. So, you know, we have our own water system and water treatment plant. We have instruments that need to be kept cold with liquid nitrogen to keep them in good shape. We need to make sure that the buildings stay, you know, watertight and you know, heating and cooling systems continue to work. So most of our staff are actually, we're still working as normal. Who were not working as normal were the resident astronomers like myself. We are non-essential personnel. So starting on the 17th, we were unable to go into our offices or to the telescope buildings. It also meant that any telescope that required a human operator could not operate. You know, but our robotic telescopes could continue. So our staff that were managing things, so we have 3 robotic instruments currently on Mount Hamilton: the automated planet finder, Katzmann automated imaging telescope, and PanoSETI. You know, there was reduced support if things broke, and of course things break. So we had to wait till we could get permission to have the right staff with the right expertise to go in and fix things, because operating telescopes is not an essential function. And I'll talk a little bit about what research they continued to do with the early shutdown in just a minute. The Shane telescope and the 36-inch Lick refractor were not operating because they required operators. But our telescope operators that work nights were still up all night because they needed to help manage things for the security of the buildings, monitoring weather for the robotic telescopes, do any emergency maintenance, things like that. All the support astronomers like myself working from home, so we could still get phoned up, log in remotely on our computers to the telescopes and help fix things. But we had a lot of things that just stopped completely. My favorite instrument, because I work on it a lot and I helped design it, is the Shane Adaptive Optics System. Adaptive optics is a technology where we look at how the atmosphere is blurring a star, and then in real time, using a little deformable mirror, a mirror that can change its shape a couple thousand times a second, to put equal but opposite turbulence on the light so that it gives us nice sharp images, sharper than the Hubble Space Telescope when everything works the way it's to be. And there was an upgrade to its wavefront sensor, the thing that measures the turbulence. And we were only 2 weeks away from finishing the upgrade and installing it and putting it on the telescope when we had to shut down. And so it's been put on hold. Other repairs are including the tip tilt camera repair for the adaptive optics system. We also had a new guide camera we had purchased for the Shane telescope, and we're busy trying to install it and get its software running. That was put on hold. And then we had DARTS, a new spectrograph for our automated planet finder telescope, is in process of being built and designed. And so that all stuff has stopped. It's now slowly coming back online now that things are easing up again. But it was very frustrating to not be able to do the work we all enjoy. So what science were we able to get done during the big shutdown? Well, the main thing was our automated planet finder, second largest telescope on Mount Hamilton, 2.4 meters in diameter. And it uses the radial velocity method to discover exoplanets. So like very similar to those spectroscopic binaries, we're looking at the Doppler shift as the star wobbles towards us and away from us because of the gravitational tug of a planet. Now, back in 1918, it was a challenge to measure, you know, the velocity of a star down to 1 kilometer per second. To discover a planet around another star, you need to be able to measure the velocity of the wobble down to maybe 0.5 meter per second or 1 meter per second. Much higher precision, but the technique is pretty much the same. Oops. So you measure the wobble. You don't see the planet directly, but you detect it. Now, Lick Observatory had done this sort of research with the Shane 3-meter telescope before, and of the first 100 planets discovered around other stars, Lick Observatory had discovered about 2/3 of them, maybe as many as 3/4. So world leaders, but we had to share the 3 meter with other observers. So building the automated planet finder, so we could just do this research to discover planets all the time on its own, was a great benefit. But you can imagine how accurate that spectrograph has to be to see these little shifts that are 1,000 times less than what they were measuring back in 1918. The second project that the Automated Planet Finder has continued to do is be part of the Breakthrough Listen program. And this is an exciting program funded by Yuri Milner, and supported by Stephen Hawking while he was still alive. But we're looking for laser signals coming from one of these planets or civilizations that might be intelligent out there. And since we know the stars we're looking at have planets, there might be laser signals. And it's actually, all this data is public. So you can go through to the breakthroughinitiatives.org open data search website and enter Automated Planet Finder and start looking for stars and data and seeing if you can detect those faint transient laser signals that might be used for laser communication between planets or between space probes in their solar system. So it's very exciting. No one's discovered anything yet, but there's an awful lot of data that's just waiting for someone in their quarantine time to look through. So, and related to the search for extraterrestrial intelligence is PanoSETI. This is our newest instrument on Mount Hamilton. It was installed earlier this year. You can see the 2 cameras sitting at the bottom of the slit of our astrograph dome. So the Carnegie Jewel astrograph telescope sits in this dome. It's not currently being used, and the dome just sits pointed south all the time. And we just open it up, and the sky drifts over these cameras. They're wide field cameras, and they're using these cool devices called multi-pixel photon counters that are sensitive from the near UV all the way to the near infrared. And they're looking for pulsed signals coming from the sky of lasers. So PanoSETI stands for Pulsed All Sky Near Infrared Optical SETI. Very cool program. This is a test program run by Dr. Shelley Wright at UC San Diego. She's been involved with SETI since she was an undergraduate at UC Santa Cruz, and she's now a faculty member at UC San Diego. And what she ultimately plans to do is have cameras like this set up viewing the whole sky all the time and put them around the world. So we're looking for laser signals from other civilizations all the time, day and night, around the world. So very exciting, and it's always exciting to have new toys on Mount Hamilton. And then our last automated telescope is the CATE, the Katzmann Automated Imaging Telescope. This is a small 30-inch robotic telescope, but because it's small, it can move very quickly. And it can look at many hundreds, maybe even 1,000 galaxies a night. And it takes a picture of the galaxy and compares it to one in its library taken the night before or a couple days before to see if there's a new star, because it's looking for supernova explosions. And here are a couple sample images of kind of oldish images, but this is discovering supernovae all the time. Back in 1998, when it first came online as fully automated, it was the world leader in discovering supernova explosions. It was discovering more supernova explosions than all the other telescopes in the world combined. There are 2 main types of supernovae. There's type 1As, like the one shown on the left here. That's when you have a white dwarf star that ends up with a companion star that gets expands to, say, be a red giant, sorry. And it dumps material onto the white dwarf. When the white dwarf hits 1.4 times the mass of our sun, it explodes. And you will see a new star appear in the galaxy. Because it always explodes at the same mass, the same brightness. So if you see one that's really bright, you know that galaxy is close. If you see one that's much fainter, you know the galaxy is far away. And so we can use these type 1A supernovae to very accurately measure the distances to galaxies. Type 2 supernovae are when a supermassive star, much more massive than our sun, runs out of fuel at its core and explodes at the end of its lifetime. And so this little animated GIF here, you can see that when the star first explodes, they get really bright really fast, and then it fades over months. Supernova 1As do similar things, but the light curves are somewhat different as we track their brightnesses over time. They're all interesting. And of course, when we're regular operations, we'll discover them with the Kate telescope and then follow up the discoveries with the Shane telescope. Not quite the normal mode of activities during the coronavirus challenges and crisis we have. But we were going to do everything we can to get our other telescopes back online. So on March 18th, we started work on what we called the pajama observing software, so that people could run the software to operate these major research telescopes from their own home on their own laptop or home desktop computer. And so we're calling it the pajama software for fun and quick reference. And then we, after it took us a few weeks to get everything working properly, but on April 14th, on our nickel 1 meter telescope, we started our pajama observing. By May 15th, we actually had the pajama observing mode running a test mode for the Shane telescope. And then just this week, we've managed to get our CAT telescope back online. Unfortunately, we've still closed to the public because everything with the coronavirus is still so uncertain. So who knows when we'll actually reopen our visitor center. Anyway, the Nickel telescope is our 1 meter telescope named for Anna Nickel, who donated $50,000 for its construction. Sizable telescope, you can see me next to it just for a sense of scale. It was initially shut down, but it's because you don't need a local operator. It's routinely operated remotely from the various UC campuses by undergraduate students. You just needed to get the software working at home. And so we started that, and some of the first projects was following up these supernovae discovered at the Kate telescope, as well as other telescopes around the world. So this is some of the early supernova data, supernova 2020 HLA. So if you can see my cursor, the arrow is pointing at the supernova, and then its host galaxy is the fuzzy thing right above it. But this software is great because you can control the science camera here. You've got telescope controls over here. We have a video camera in the dome, so you can look at the telescope, control the shutter and the mirror cover, all these good things. We even can pipe sounds to the home so that you have all the dings and beeps and whistles that let you know your exposures are done or in progress, or wake you up at 3 a.m. when the nighttime drowsies hit. So great science going there. The 3 meter telescope, as I said, we started testing the pajama software and everything starting May 15th through May 28th. That's the permission we got from the county and UC Santa Cruz administration. And then we had to stop, but the requirements, because we can't have more than one person in the dome at a time at that time, we couldn't change instruments. So luckily, our most commonly used instrument, the CAS spectrograph, was mounted on the telescope, and that will remain mounted on the telescope until such time as we can have enough staff working in close proximity to change instruments on the telescope. Of course, this picture here on the right, where we're not socially distanced, I took this photo in December of 2019, which shows most of our mountain staff on Mount Hamilton. Anyway, our regular science operations with the Shane, we resumed on June 24th. In the interim, we were given time to do some testing of our new guide camera. So we have a brand new guide camera we started using as well, which is more sensitive and really a joy to use. But here's some of the first data we got out of our Shane telescope, which was of another supernova, because our supernova group is very active. So this is supernova 2020 JFO. And so if you look at this data, the vertical line through here is actually the supernova. The horizontal lines are the images of the slit showing atmospheric emission or absorption lines, or in this case, mercury lamps in San Jose and sodium lamps in San Jose. Now there are two traces here, two spectra, because this was an interesting supernova. They wanted to look at the polarization of the supernova. So just like they were studying the polarization of the solar corona back in 1918, we're still studying polarization today of astronomical objects. And so there are two images here of two different polarizations taken at the same time. So exciting research going there. And again, more controls so that the observer can sit at home. And then finally, our last telescope that we got online just earlier this week was the COUDAY Auxiliary Telescope. And this, I just added this slide today because today is the Parker Solar Probe flyby of Venus. And so it's doing a few flybys on its way to close encounters with the sun. But today, the Parker Solar Probe, instead of looking at the sun, was looking at Venus's dark side, trying to see any auroral emission from solar wind interactions with Venus's atmosphere. And so we also are looking at the dark side of Venus with our COUDAY Auxiliary Telescope with the high resolution spectrometer. In fact, this is the same spectrometer that discovered those first exoplanets using the radial velocity technique many years ago. And so most of what you see of Venus is, of course, a solar spectrum. And so there are lots of absorption bands here from the solar spectrum. But they're looking for particular emission from oxygen at the right wavelength from the aurora. And so my new colleague, John Reese, has been trained on how to use the CAT telescope. The CAT telescope is not remotely operable. So right now, because of coronavirus, only the local resident astronomers, and there are only 3 of us, can get into the domes to operate a telescope. But similar data is being taken over these next few days with the Keck telescopes and the Apache Peak observatories to coordinate with the Parker Solar Probe. So very exciting new data, and who knows what we'll discover. When it comes to reopening to the public, we have a phased plan. Right now, we're sort of at phase A, which is opening some of the outdoor areas to the public and enabling gift shop curbside shopping. I'm hoping that in the next week or 2 that we'll have phase 1 ready. However, opening the visitor center to the public again is more challenging, especially with COVID cases going up and the crisis currently right now not looking very well controlled. But we are planning to have one-way passage through our visitor center and monitoring people, having people wear masks and all, have hand sanitizer available, all those public health and safety things. At some point, we'll be able to have normal operations and people looking through the 36-inch telescope. But right now, of course, people tend to touch the eyepiece, put their face up to it. Right now, that's a germ magnet and very unsafe procedure. So I have no idea when it will be safe enough for people to view through the telescope again. And then at some point, I hope by next year, we'll be able to resume our public concert series and telescope viewing programs, as well as our private events like weddings. So finally, I'm going to advertise a couple of things. Every other Monday, we have events. So on Monday, July 20th, we'll have a living room lecture. Dr. Shelley Wright, who I mentioned earlier in the talk, will be presenting about searching for extraterrestrial intelligence. It's at 4 p.m. There's a Zoom link, as well as it'll be visible on our Facebook page. And we also have Ask an Astronomer. And that'll be on Monday at 4 p.m. And Dr. Alex Filipenko, who is the head of our supernova observing team, will be answering any questions. If you have astronomy questions you have a burning desire to have answered, submit them to social@ucolic.org or via our Facebook or Instagram social media pages. And we'll see how many questions Alex can answer for you. So these are alternating every other week to keep our public engaged with Lick Observatory, since you can't come up and visit us in person right now. So finally, please stay safe, stay healthy until we can actually meet in person. We're working on how we can manage everything, do more science, get the public back up here with the current crisis, and especially when things are relaxed. But in the meantime, wash your hands, wear a mask, stay home as much as possible. And we'll get through this. So thank you very much. Stop sharing.
Great. Thank you very much, Elinor. I want to see if we have any questions. Oh, by the way, I think we were looking at 2020 JFO on the same night. There's my
Probably. It was a good
Yours
one.
was higher resolution. Gary asked if you've noticed up at Lick if there's any drop in light pollution as a result of what we're going through now, closing of businesses, car dealerships, that type of thing.
I can't say we've noticed anything like that. I think in terms of, you know, the car dealerships and stuff, which are some of the big problem children when it comes to light pollution, they've been leaving lights on for security just like normal.
Oh yeah, I guess they would, right?
But we haven't been observing, so it's hard for us to measure the change in light pollution as well. So there's a lack of data there.
Another question, Sujay, who gave our talk earlier, he wanted to know how is the observing schedule for these telescopes for submitting observations? Will the telescopes be imaging for research groups? How is the scheduling of the telescopes changed as a result of all of this?
So the scheduling of the telescope hasn't particularly changed. We do have a call for proposals every 6 months. So we schedule our telescopes pretty much on a 6-month basis. And you get your assigned nights from the proposals that have the best reviews, get maybe all the time they ask for, you know, et cetera. So nights are doled out. Because of coronavirus, when we shut down, it was like when it rains on your night. Sorry, you don't get to observe. Try again next year. Apply again. There are no rain dates. The telescope time is oversubscribed, so we have more astronomers asking for time on our telescopes than is available, particularly for our 3-meter and APF telescopes. The 1-meter telescope is a little more flexible. So you know, there's not necessarily, like, we canceled a lot of the nights because of we canceled our public programs, which opened up nights for observers to use once we got our pajama software running and they could observe again. So, but yeah, it's been a challenge and it's been very disappointing. You know, a lot of projects just stopped and there's a lot of lost data and you can never get that back. So it's been affecting professional research around the world.
Related to the pajama software, I mean, are you, when you're using it, I know all the things that can possibly go wrong, and you know there's always something going wrong. Is there a staff member present with the telescope while it's being used, or are they just like on call, like I can't close the roof, or I can't do this, or I can't do that?
So that depends on the telescope. The 3-meter telescope has a dedicated telescope operator that's there with it all night. So they're the first line of defense if there's a problem with the 3-meter or any of the other telescopes. And then the support astronomers are the next people to contact so that we can go in and try and fix something, reboot a computer, you know, change a fuse, try and figure out, we're master troubleshooters. Sure. And so we can very quickly identify where the problem is and repair it as quickly as possible. So yeah, that's the nighttime crew. So the support astronomers are on call. So you phone us in the middle of the night, and our telescope operator for the chain is awake all night long while the telescope's in operation.
Okay. Don is asking, was the elevated floor in the 36-inch repaired?
Sadly, it has not been repaired yet. Oh. We keep it. It's a big challenge because of its age.
It's the hydraulic system, right?
It's a hydraulic system that we're actually, the current plan is to replace the hydraulic system with a modern screw stage lift system, more akin to what they use on, say, aircraft carriers to make those platforms go up and down. But the problem is we have no original drawings. And so we actually have someone planning to come in with a laser scanner. And that, of course, was stopped because of COVID and they couldn't come up. So
you have to reverse engineer the whole thing before you can even begin to consider a replacement hydraulic system.
Yeah, so
oh, man.
It's a big challenge. We're working on it. I really do hope that we'll get it finished sooner rather than later, because operating the 36-inch, which I do, is so much easier. We can just ride the floor up to the telescope. Yeah.
So has seeing conditions improved due to SIP? I don't know what SIP. Oh, shelter in place.
Yeah. So
a whole bunch of new acronyms to remember.
We haven't, because we haven't been operating, with our largest telescopes, we don't know a lot because it's our largest telescopes that we usually keep the seeing statistics on. However, I don't think we've seen any real differences, because usually the pollution and such stays in the valley below Mount Hamilton. We very rarely have the pollution in that marine layer come up as high as Mount Hamilton. So our atmospheric conditions, I would hazard a guess, are pretty much the same before, after, and during COVID. Yeah.
Okay. Well, I think that's it. I don't see any other questions. So thank you so much for spending time with us tonight. That was a great talk, and hope to see you up at Lick when things improve.
Yeah, definitely come visit us.
All right. Best of luck to you.
When we can. Thank you very much.
All right. Take care now. Thank you everyone for attending tonight.